Hi and welcome. If you were in yesterday's session on NetOps Coding 101 and received a USB key, we're going to be reusing that today. If you did not get one, or if you're new today, please raise your hand. We're going to be handing out USB sticks, which have a virtual machine that we'll be working with throughout various lab activities. But TJ up here has got a whole handful, and so does AJ as well. So we're going to go and first get started by giving those out to everybody. So good afternoon, everybody. I'm David Swafford with Facebook, and today we're going to be walking through NetOps Coding 201, building auto remediation for your network. If you had just walked in, I briefly just made a quick announcement, in that yesterday in the 101 class, we gave away USB keys with a virtual machine that we used in various lab activities. If you have that from yesterday, the USB key we're giving out now is the exact same one with the exact same content, but there's additional files and content on that we'll be using today. But if you did not get one, go ahead and raise your hand so that we make sure that you can get one from TJ or AJ, who's walking around in the back. And then that way you'll be able to code along with us as we continue on. So out of respect for time, I'm going to go and get started while TJ and everybody's handing those out. But feel free at any time during this, if you have issues during either the lab activities or if I'm going too fast or anything, please raise your hand. We have several people here helping us, so that way you can get the most out of this. But again, welcome back, and thank you for sticking around with us for one of the last sessions of NANOG. This has been a great NANOG this time around. So today, this is the 201 session. We're going to continue with our theme of automating the detection and remediation of network faults. But if you were in yesterday's session, you might have learned quite a bit about the initial portion of this. For example, parsing syslog messages with regular expressions. We're not going to be thinking about regular expressions anymore today, so hopefully you got your fill yesterday. But we're going to be looking at another side of this. For example, focusing today on building the system of what is modeled after something we use at Facebook called FBAR. And if you hadn't heard of this before, FBAR is the system that we use to react to network faults and handle all the initial troubleshooting and diagnosis for us to free us up from the time that we would normally type just in the initial show commands and such. So our goals of today's session, though, are to empower you in a way to build a system that is organized to support hundreds of remediations. If you were in yesterday's session or remember the one from last year, we worked with 2 remediations. So 2 remediations is manageable in a small Python script. But as you start thinking about 100 of them, one Python script doesn't quite make sense anymore. You could put 100 remediations in one script, but you might find yourself with a script that's now 10,000 lines of code, and that becomes a little bit cumbersome. So we're going to look at some ways to make this organized from the beginning so you can set the foundation right. We're also going to talk about one issue that a lot of people might hear with when you talk about Python in terms of performance. Specifically, we're going to talk about how to make this react to hundreds of events at a time. Yesterday, we were working on one by one, using a for loop, for example. So we could only act on or try to troubleshoot one device at a time. But some devices are slow, and you might have thousands of devices. So we're going to show you as well how to handle that. And finally, the content and the design of this is meant to be built in such a way that it can be managed by your entire team without having any sort of software engineering or CS background. Something that's very key to this model or this approach that has helped us at Facebook as well. But first, let's talk about how this works. A quick little diagram. So we have 2 network devices here plugged in. They have a network link, and we have, for example, an Ethernet link. Let's say we have an outage, something all common to us, such as a fiber cut that takes down 1 or more links. Well, in this case, the device sees that link going down. We get a message logged locally, for example, in show log of, hey, this link went down. A message something like this, IF down, link failure. In the case of our system at Facebook and what we're basing this off of, we collect all of those log messages on a central syslog server. And then we have a piece of code that we're going to just call the parser, or parsing engine, that is looking at those log messages and using the regular expressions we worked with yesterday to kind of parse out the data from those. And finally, the parser is then injecting what it finds as events into a database. This is where we're starting to build something a little bigger than what we started with yesterday. So yesterday, we had this idea of a basic parser that then started running remediations as it found things and tried to run them serially. Now we're starting to add a database in the middle that will be basically our queue or communication channel between components of the system. And so we now have an additional piece called the event processor, which simply fetches new events from the database to work on and process. And events here are more just generically your faults or any kind of issue that you might have parsed. And then it tries to locate remediations to run against those to try to do things such as shutting down a bad link, or something as complicated as redirecting traffic around a faulty device. And finally, saving the result. So the focus of today's session is on this piece of the system. We're not going to be dealing with regexes anymore. We're going to be dealing with now the other side of this, which is how do we use a database in this, and how do we fetch and run a bunch of these different remediations at once, and also how do we build this with structure and organization. So at first, though, that slide was pretty and all, but I do want to show you that this actually works. So we have a quick demo that I'm going to show you, which is a new version separate from yesterday. So this is a new version where we're showing you all the different pieces. So one thing, on the USB keys that you've been given, there is actually a virtual machine that we're going to dive into in just a minute. But one of the things that is different about this virtual machine from last year's is that we are now running MySQL Server with the database already pre-configured, which is how these components are going to talk to each other. One thing I did not mention on the slides, though, is that I don't have a live network to prototype against right now. So included with the VM and on the USB stick, we put together a syslog generator to arbitrarily generate random messages to kind of simulate a load to play with, for example. And so I'm going to get that started just in this one tab right now so that we have actual syslog messages to work with. And so in my second tab, I'm going to simply just show you that log file in real time. And so we have this syslog generator writing to /temp/messages. It's randomizing the date and time and even the device names and everything down to the IP addresses that we see. But it's generating messages similar to network devices that you might see. Now, this code exists on the VM, and you have it to play with. We're not going to go into that, but it's there simply for prototyping against. But now that we have syslog messages being generated from this, I'm going to start up the parsing engine. And so what I see in this tab, this is a slightly improved version of what we were building yesterday, in that it's now reading that log file in real time, /temp/messages. And it's trying to continuously read it, trying to parse those into events, for example. And then it's actually talking directly to the MySQL server running on this virtual machine and creating new events with the data that it's parsing out. And so if we leave that running for a little bit, it's going to create maybe a few hundred, few thousand events. I'm going to stop that for just a second, just so that we don't kill the VM that's on here. And so now on our database, we should have a bunch of events in there. Just to prove that it is real, I'm going to show you that. Actually, that's a little small. I'll make it bigger. So I'm just hopping into the MySQL shell right now. We're just running MySQL server. And there's a database there called FBAR, which is just the name of this version of it for today. And I can take a look, and if you were in yesterday's session, we talked a little bit about building a database to describe this. We're not going to dive too much into building the database again here, but I do want to show you that this does exist and it's not completely made up. So for example, we can do show tables. We have a table called events here. We can describe that table and take a look at what it looks like. And it might look just familiar from these events that we were working with. We have a timestamp, a device name, error code, and so on. And just to get an idea that we actually have some events, we can select the number of events or entries in this table that have been populated. And so right now I have 5,780 events to play with. I think that's enough to get started with for this lab. On your VM, you should actually already have about 3,000 before running anything. So that way, as we get to the activities, you don't have to worry about running the other pieces yet. So now to show you it in action, though, I've only shown you the first pieces of it. I've shown you the parser. We've got data in a database, but now we need to act on that data. So I'm just going to run this thing called processor.py under the 201 directory. You'll see what we're working with is actually code under net FBAR, and then the different pieces are under different subfolders. But what I see running right now is actually a lot of stuff scrolling on my screen. But what we see is that we're actually trying to remediate or work on a bunch of fictitious devices at once. Now, something interesting to note here is that if I didn't have a remediation to run, I did put one to run as a default. And it's arbitrarily sleeping anywhere from 1 to 12 seconds. So each of these remediations is actually sleeping in the background. But I'm not running one by one. I'm actually running several at a time and trying to react to or think about them. So these could be something as simple as debugging PHP adjacency changes or link down events, or something as interestingly as a default that then escalates to your knock of things that haven't been remediated against or haven't been handled. So that was just some food for thought, though. But what we're going to be doing today is actually building the second piece completely live, the event processor. And I apologize for jumping back and forth. Hopefully that doesn't make you too dizzy. But we are going to be doing that a little bit. But before we get started, though, I do want to walk through quickly for anybody that's new what is on the USB key. So the way this is going to be structured is that the first half, I'm going to walk through more of food for thought and design and ways to improve the system. And then the entire second half, we're going to be building that processor component entirely live with IPython, down to everything you saw there, where we're even running multiple things at once, talking to the database, and so on. So to make sure that we can get on the right foot, though, we're going to be using this virtual machine that's on the USB key. I'm not going to spend as much time in this today because if you were in yesterday's session, you've already seen this and you spent some time. But what we have is a virtual machine of Ubuntu desktop. The virtual machine is actually a virtual appliance which works with both VirtualBox, an open source product, or VMware. So if you have not already installed either, the installers for VirtualBox are on the USB key. But if you have one of those installed, you should be able to import this virtual appliance natively into either VMware or VirtualBox using, for example, import appliance from the menu there. And it should take a few minutes to come up like this. I'm going to take just a minute break here, not nearly as much time as yesterday, to make sure anybody trying this can get caught up. But then I'm going to continue on, and if you have trouble or you get stuck on this, please raise your hand and we'll make sure that somebody can help you through. And while we're taking that quick break, are there any questions so far on what I showed you? Does that make sense, what we're trying to do?
Not on what you showed us, but is it possible the PDF to be posted on the NANOG site for what you're going through here?
I don't know. Is anybody from NANOG here about the PDF?
Usually they're pretty good at that. I'm here, but I can't hear what he said.
Oh, he was asking if we could get the PDF posted for this session?
Yeah.
Okay, cool. Thank you. Sweet. So I'm going to continue on, just out of respect of everybody's time, because some of this is repeat from yesterday. So looking at VirtualBox, once we get started, we'll be in this virtual machine that you just saw me working with. So now getting started. Let me grab 1 second. So first, let's talk about a little bit about building the system to be in a way that's going to make sense in the long term. And the reason I want to start with this is that we have this system at Facebook that is doing a lot of work for us called FBAR. And it reacts to a lot of faults, and it handles a lot of the background noise. But it's been an organic system grown over many years. So as a result, it's a little bit messy. For example, we have a lot of remediation stuffed in single files. And we have several files that are several thousand lines long. To a new person, that is very scary to look at. Even though you're only changing or adding a small section, just thinking about thousands of lines can be cumbersome and scary, and it doesn't have to be, though. But before we get into that, let's talk about a few other things, and talk about things we were using yesterday that we can improve on. So yesterday we looked at parsing out the regex of the syslog, and we got back what we call a tuple, where we had, for example, the result of the match as the date, the time, the error code, and so on. Using tuples in Python is not a bad thing. But in the case of this system, we can actually do better. The reason I'm pointing this out is that if you start to work with tuples, you start seeing code like this, where you extract the tuple directly by calling something that has the tuple. For example, this line right here. This will work fine until you need to change the way the data is either organized, or where you either add or remove something from the tuple, or you think about more than one vendor. For example, this fictitious vendor has a format like this, where the date and time and device name are in that order. But if I start adding server logs in here, the server logs may look different, which means that when I extract the elements, they're not in the same order anymore, which is something that we should not have to think about if we can avoid it. So one example to compare, an example of adding something and what happens there is that if you forget to update all the places that are using that tuple, for example, if I add a status code in the middle, well, my code will crash if I forget a place, and it'll crash like this with the value error. But we can be more prepared. We can be prepared for this change and not have to think about it. So one way we could do it is we could represent this event differently. We could use a dictionary, which is another data structure in Python, which has a key value pair instead of this positional comma-separated list or so. This will actually work fine to represent our dictionary. But I want to show you another example that might make a little bit more sense as you start to think more of a bigger system that you're going to be on call for potentially, and you might have multiple people responsible for. We have these things called objects in Python. Now, I'm not going to bore you or go deep into object-oriented programming because it's a very big topic on its own. But it's a way to describe, for example, attributes with an entity. So for example, I have a variable here called e, which is described by the object of event. And that event takes in specifically attributes or parameters of timestamp, device, error code, and error message. Now, this looks right now very similar to a dictionary. But what's interesting about it is when you start to think about a system maintained or built for more than just you. Because ultimately, when you're automating yourself, you want to do cooler things, but you do not want to be the only person responsible. You want your teammates to be able to add to and supplement this and understand it. So that's where documentation is nice, but many engineers hate documentation, myself included, because I would rather write code than write a wiki page, because the wiki page will be outdated. But this is where, for example, you can use an object to actually help you. And I'm going to come back to this because I skipped actually a section. So this is actually where an object makes sense, though, because you can describe structure and enforce structure by code. So it's self-documenting in that when I see this class here, this is describing what every instance of this object looks like and feels like. And so it says right now, when I create this, I have to at least have a timestamp, a device, an error code, and error message. What's really cool, though, there is that I can add sanitation or sanity checking to this. So for example, yesterday or in the prior slides, I separated out the date stamp and the timestamp as two different things. I thought about this problem as I started putting this slide together because having the date stamp as a string and the timestamp as another string sort of works, but when you start talking about a database, it makes it a little tricky to compare. So one thing that's really common is to use standard like Linux time, for example, which is represented as a single integer, which is what I'm doing here. It would actually be pretty cool to sanity check that when I go create this instance of this event and say, is that actually an integer? Because if it's not, my code later saving it to the database would crash. So it would be better to catch that ahead of time. That's actually probably one of my favorite uses here. Going back 2 slides, because I actually skipped over this. So when you look at dictionaries, we showed that yesterday where you can access values from a dictionary using that bracket notation. Objects are very similar, but instead of using that notation, you have this dot notation, where you say the variable name dot and then the attribute, for example, device or error code. And so it feels and it looks just the same. But now we have these other 2 potential benefits. I do point this out because the system we're using is based on objects here. And specifically, if you look in terms of folder structure, netfbar/lib/db.py, you'll see a class there called event that actually has some of that sanity checking and a little bit more advanced error checking to give you some ideas to run with. So talking about this VM, what have we already staged? There's a little bit of magic there. So if you take all this code and try to run it elsewhere, you're going to run into a few problems, but I want to explain what those problems are so that you can get over them. The one is we've pre-staged a database in MySQL Server. We've already pre-staged an events table that I was just using. we've added specifically a library for interacting with MySQL, that db.py, which is different from the one used yesterday. Yesterday, we talked about SQLite. So there actually is still the SQLite library. Whoa, sorry. So there is still the SQLite library from the 101 class. But today, we're actually using MySQL server to show you a little bit more advanced real-life system. So it's a separate library. And all of today's code is under that NetFBAR directory. And finally, we're using a bunch of different directories. And if you're new to Python, this is something that might be a little confusing at first, because when you have a bunch of files, it's really easy to use a bunch of files if they're all in the same directory, because you can just simply import them using the standard notation of import the file name. But when you start adding files and you start adding complexity, it becomes a little tricky, but it's not that hard. So what we did to make that work is we created this as a package, or a package with sub-packages, so that our import statements are actually working with the file paths. So you'll see later that we use things such as from netfbar.lib import db.py. And we're doing that via the package notation. And I point that out because with using packages, you have to install them. So to run this code elsewhere, you would have to run through that. So stepping back a few of the pieces, though, if you were to try to reproduce this or rerun this, the script to set up the database is actually a bash script in the VM and on the USB key. You'll see dbsetup.shell. And that simply creates a username for NetFBAR. It creates the database. It creates the initial table structure. And this will also blow away the database if you want to start over and trash the current one and start over and reset it. Again, I mentioned we're using these packages in Python to install them. It is simply just running the Python interpreter against the setup.py file in the base directory with the word of install. Very simple notation, but it's an easy thing to get tripped up on as you're diving into this kind of stuff. But don't worry, this has already been installed for you, so you don't have to worry about this for today. OK, cool. So now onto the first piece of this, the parser. Where to find this? This is under netfbar/parsingengine/parser.py. It's a slightly bigger version of what we built yesterday in the demo, and we're not going to repeat that. So I'm simply pointing out here where the file is. So that way, if you wanted to dissect the code, you have a reference point. Now let's talk about remediations. So remediations, again, are just simply the logic that we use to describe our workflow of troubleshooting a network problem or a network fault. It could be something as simple as a line card going down and using that event and our remediation code to go collect the logs that are appropriate to debug this, or simply to open a support case to have remote hands replace that. It could also be as more complicated as something as changing BGP policy to redirect traffic around a bad network device. That's actually the way we avoid a bunch of on-call pages during the night, in that our network luckily is big enough that we can just cut off network devices arbitrarily when we see enough of a problem, and then fix them in the morning or so when people are wide awake and not asleep trying to make more mistakes, for example. So looking at the remediations, though, we have a few problems from yesterday that we worked with. Specifically, yesterday, we started to see some duplication. There was not much structure, and really debuggability was not there. So one comment on debuggability. If you looked at yesterday, or if you've seen this, we were running a lot of commands with SSH back and forth. And we were evaluating that output in real time. Something really burdensome to troubleshoot as a network engineer is code that fails at one point and then suddenly works, but you have no history or no log to look back at. So something that would be cool here is some mechanism to keep track of what commands did I run against this device in retrospect to troubleshooting this specific issue. What output did that device give me along the way? That's stuff that you could capture if you had an easier way to build structure into your system so that each individual person writing a remediation would not have to reinvent the wheel and think about it again. So taking a look at how we're going to organize our remediations. If you have not seen something called the Zen of Python, any chance you're in a Python terminal, type in import this, and it'll give you a nice listing of guidelines that'll help you just build really clean and efficient code over time. One of the things I stole from that is this quote of sparse is better than dense. And so in the system today, we're going to show you how to do this, where it's built as a system of one file per remediation, where we have just a very small amount of code. And then we are going to factor out the common code to a shared module. Now, granted, you'll eventually have, if you have 100 remediations, you'll have 100 files or more. But then when you're adding or removing one, you just have a common template to work from, and you have very little code to look at or evaluate and test against. And so looking at the remediations yesterday, we kept repeating this SSH command, for example. SSH equals SSH helper, device name, username, and password. Now, granted, we don't actually need all of this here because we have a library we're calling this SSH helper module. So we could put the usernames and passwords in there. But I would hope that you're not using the same username and password everywhere on your network, and I would hope that you do not want to put it in plain text in your file. So something that would be nice is to factor this out to a common place that has some way to go look up that username and password. For example, at Facebook, we store them encrypted on a remote service that we just go query against, and then they're decrypted on the fly. All of that is handled by shared code, though, so our remediations don't have to think about that. So here is an example of doing that. So we're going to bring in our friend objects and classes here. And what I'm showing here, though, is that I can have this idea of a base class or a base remediation that describes all of the shared code that our more specific remediations are going to use or add to. So for example, I can move the SSH command to this. And if I want to think about debugging, I can add code here to keep track of those commands ran. And when it's done, I could actually have some way to go store the output, such as another database table that says, for this event, I ran this command, and this was the output. So here I now have a function called run command. And then as I look at adding a remediation on this model, this is showing the file for the link down remediation, where I have now a class of remediation that is adding to or building on top of this thing called base remediation. And that's what you see by these in the parentheses here. That means I'm adding to that existing class or that existing class, which means that any method previously defined on what I'm adding to is also available to me. So for example, now to run that show command, I just simply run self.run command, which accesses things off of this current instance. Without going too deep, and we actually are going to give away some books at the end on object-oriented programming, so you can geek out on that. But without going too deep, just trust me here in that this gives you a way to kind of make your code very concise and small. And so now one other piece, as you start to think about building this out where you have a lot of different files, you're going to suddenly have a lot of what we call import statements that we talked about yesterday, where you bring in other modules and files. And you will eventually have an import statement representing each of these files. So one clean way to kind of connect these together is that you could move all of that into its own file. And so what I'm showing right now is actually mapping.py from netFBAR lib, where we import all their individual remediations, and then we build a dictionary that says, for these individual error codes, what remediation should I run? And if you wanted to build this bigger, though, you could actually have a list of remediations here and potentially do multiple things to debug against more complicated failures. But what I've got going on here is now a key in this dictionary where it's the error code that we parsed out of the syslogs already. And I'm mapping it to specifically the module that contains the remediation, such as the link failure module or the BGP adjacency module. And then finally, in that file, I have just a helper method that says, give me the remediation based on this error code that returns what module is associated with that. This is kind of handy because now you don't have to think about all these if statements and forking inside your actual system, and you can keep it contained. So as a network engineer that might be new to the team, they could add just simply a new remediation by editing like mapping.py and adding another file and not have to think about the rest of it. It's just more food for thought there on how to make this friendly and approachable. So that's in mapping.py. Any questions so far? Cool. Oh, yeah. Sweet. So now we're going to go into the actual fun part of this, the hands-on portion. So at this point, we're going to build the rest of this live with IPython, the event processor, which is going to fetch the items that are from our database, go try to figure out what remediations to run, and then we're going to first build it slowly, and then try to rebuild it in such a way that can run a bunch at one time. But first, baby steps, starting simple. So one second here. Cool. So I'm going to actually hop into IPython at this point. If you are following the slides, everything I'm going to be typing are in the slides. But I'm going to try to type this slowly and what? No slides? Oh, they're not posted yet. Actually, if you give me 1 second, I have netengcode.com points to a Google Drive link, so I can throw them there. So if you go to netengcode.com, I'll throw a PDF right now of the slides up there, which also has everything that's on the USB keys. Okay, cool. These are actually the same ones that should be in queue to publish as well. Yeah, netengcode.com. Wait, did that go? No. There we go. Okay, 1 second. Okay, so that might take a minute or so. They're about 10 megs. Sorry for all the photos. But it is uploading in the background. So give it about a minute or two and you should have the slides. And then I'm going to walk through this pretty slowly, though, so that way we can all build this together. So if you're in yesterday's format, we went back and forth from some labs. This format is actually built where we're going to just continue live without any separate lab breakouts. So if you do get stuck as we start building, again, just raise your hand. We've got a few people that'll help you along. And I can also slow down and make sure that it makes sense, because I am sometimes a little hyper, which I apologize. Cool. Okay, cool. That should be large enough now for you to see. And then again, in a few minutes, these slides should be up. So I'm just going to get started by importing one of the helper modules. So I mentioned these are using packages called FBAR. So that changes what this looks like from yesterday, and that now everything's got this namespace of from .NET-FBAR. So for example, from .NET-FBAR, we'll type .lib, we'll type import db. And that's going to give us access to our database module to handle all the connecting to and from the database. So that way I don't have to bore you with how to connect to MySQL, because you may choose a different database, and I didn't want to distract you from that. But feel free to look at db.py to get an idea of that. And then we'll walk through with that now. And so what we need to first do is get a list of the events that have been queued up by our parsing engine that we ran earlier. And in your case, they're already queued up ahead of time. And so to get events, we need to open a database connection. And so using the database module here, we use this with statement, which might be familiar for opening files, for example. And we say with open. Oh, I'm sorry, not with open. Sorry, open is file opening. So what we say is with db, lowercase db. And then the actual class there is uppercase, lowercase db. So we say with db.db, sorry for the repeat, as dbcon. We now fetch the events from this. Yeah. And so we say events equal dbcon, which is a class that represents different methods that give us an interface to our database. And we say get events, get underscore events by status. And it takes in one parameter, which is a status code. And for simplicity, the status code number of 1 just means new events. So if you press enter, because I'm in IPython and the indentation, it wants me to hit enter again before it fetches. But if I hit enter again, it should go fetch those events from MySQL. If you print the length of events, we should see that we get back potentially 1,000 of them, based on a safety limit in that database file, even though there are potentially more. But it gives us a way to not kill the database. For anybody following along, have you gotten to this point where you see at least 1,000? If you do not see any events, definitely raise your hand, because that will be a problem later. The PDFs are up. Cool. Sweet. So right now we've got 1,000 events. So if I were to print, if I were to walk through those, for example, for Ian events, and print, I can see that now I can print what looks like the events from earlier, which is cool because now I have the data back from the database that I can start working with. And so now we want to figure out we want to at least get one of these to test, to run a remediation against. So I'm just going to grab the first item from this list. So I'll just say event equals events, and then I'll grab the first element, which is at position 0, like that. So if I say event equals events 0, and then print event, I should get back just one event now, which makes it a little easier to test, because we want to make sure at least one works before you make it faster and try to make it better. So we've got one event. And for example, and your event may be different based on the randomization going on. But in this event, I have a vendor or a switch that's out in SJC that has an issue with, for example, spanning tree, edge port, and BPUs being seen. Hopefully you're not running layer 2, but you might. So let's try to figure out what remediation, though, to run against this. So to figure out, using that mapping that we have already, well, we first need to import that. So from netfbar.lib.remediations, we're going to import a file called mapping. And go ahead and try that. And so now we're going to look up now which remediation is mapped to that error code, if one is mapped to it. So to do that, we're going to say remediation. Actually, we're going to give it a different name here, and I'll explain in just a minute. We're going to say actually class equals, or CLS equals, mapping dot get remediation, and we're going to actually pass it specifically the error code from that event. And we do that by saying event.errorcode. And assuming you get no errors here, we should be able to print class and see what we got back. Did everybody get back something on this? Either a default remediation or one of the more specific ones? So at this point, I have back now a reference to the class that describes that remediation, but not actually their remediation yet. So to get that, I need to actually pass in and create an instance of this class, for example. So class here is similar to what we saw event earlier, where we had to create a variable that is of event. That's similar to here, but we don't know the way. This is kind of some magic underneath here, in that it's returning me a reference to it, so that I don't have to think about or know what name or what file I'm getting it from. And so now to get an instance of that represents this remediation, we can do remediation equals CLS, and it takes in the initial event when we create it. And so if you print remediation here, you should see back that it prints out the name of that remediation. So in this case, I got back the default remediation, meaning that there is not a more specific one. Cool. So at least I have some remediation that we can go try. So now we need to do something with this remediation and actually test it. So to run the remediation, since we're using the structure of the base class and the individual classes, they all implement this method called .run. And so to get back a result, we simply say result equals remediation.run. And since we're using an object here that already knows about the underlying event, this event in specific, based on the fact that we passed it in right here, we don't have to tell it anything about this device or this error code or the time, because it already has that in memory. It knows that because this specific variable for remediation actually represents a remediation attempt for only this device. So as we have, or only this device in this event. So as we have 5 events on the same device, we would actually have multiple variables that represent that, which keep track of the state separately. But at this point, I ran one remediation. And since I'm running the default remediation, there is actually not much verbosity there. It's not printing anything. But it does have arbitrary sleep statements added to delay running it, so it feels like something. And it is randomly returning true or false to mimic whether or not it succeeded or failed, so you can evaluate that. So if we print result here, we see that remediation attempt failed against our fake device out in SJC. If we run it again, it might successfully pass. Who knows? But anyways, the point here is we just ran some remediation logic, which could be, again, as simple as checking interface stats, shutting down an interface or whatnot. And you can build to your heart's content on that idea. So now we run one remediation. That's kind of cool, but not really, because this actually took a lot more time than just hopping on that device and troubleshooting. So what we ultimately want to do, though, is we want to save ourselves time. So the next step here is we're going to build now a function that is going to go run that remediation and figure out which remediation to run. So if you're following along, I'm just going to create a new function using this def keyword, and we're just going to call it process event, for example. And let's make that take in an event as the input. And if you're following on the slides, I'm currently on slide 93 right now. And so def process event is going to do everything we just typed, but under this method. So this is a little repeat, but we're going to say class equals mapping dot get remediation, and we're going to pass it in that error code. And then we're going to grab back an instance to represent this specific remediation attempt using remediation equals class, and then pass in event as we create an instance with these parentheses. And then the result, again, back from remediation.run. And then we'll return back the result to whoever calls this function. Oh, sorry. And if you screw up, IPython lets you just do up arrow, and then you can backspace and change things. And so what I meant to say is result equals remediation.run. I left off the equals there. And then we return the result. Cool. So we haven't ran any of this code yet. It's just now a function that we can run at will, which is cool, though, because as we're walking through the different events, we don't have to rewrite all of that code. So what we could say is we can first test this with the one event by saying process event for that event. And again, since it's running that default remediation, there's nothing printing on screen, but if it were debugging things and printing stuff, we would potentially see that. But it is arbitrarily sleeping just for the purpose of this demo and returning me back true or false. So we've now ran a remediation against one device and gotten back something. So let's start building this a little bigger, though. So let's actually start iterating over our list of events, for example. Bringing back our friendly for loop. For event in events. And we can at least look at processing them one by one first to test this out, saying result equals process event. And then we probably, at this point, want to start adding some debug output so we know what's going on. Because we're going to grab 1,000 events and do something. It might be useful to know why our script's hanging and sitting there. So it would be good to say, for example, print event.device. The error code and potentially the result. And so at this point, this is somewhat similar to yesterday in that we're walking through one by one and running these remediations. So it's not much different yet. But we've got kind of the foundation set. Because now we've at least gotten the first 1,000 events from the database. We're now walking through and trying to process or act on those events one by one. And then we finally are at least given us some debug options and debug output. That's cool, but I'm really impatient, and this is way too slow for me. Hopefully you're getting impatient as well, because this would just drive me crazy to look at. Even though it is typing commands probably faster than you might be typing, like I just still can't send it. So let's make this better. Let's make this better. But before we try to make that better, and I know I just scrolled off screen, are there any questions so far? Okay. And if you are stuck, again, just raise your hand. We want to make sure that we get you unstuck and able to continue. So let's take a look at how we can make this better and make this faster. So we have a few options with Python. There are modules called threading, multiprocessing, some of the newer stuff called async IO, one that's not quite as new, but a little bit newer depending on who you talk to, called gevent, And depending on who you talk to, they might just tell you to get rid of Python and go to Go or another language. All perfectly valid options depending on the use case. For example, the NetNorad agent that Peter Lapkov was talking about on Monday that we open sourced was originally in Python and is now in Go. That was doing some really heavy lifting, and there were some actual limitations where it just made more sense. But think about it, if you already know Python, it might just be easier to write a little bit slower code in Python if that's what your team knows. So be cautious of the learning curve there. But it is good to know some of the advantages and some of the disadvantages of these to know what might work for your situation. So I actually started building this demo originally all based on async IO, one of the brand new things out there. And I will admit, I am not traditionally from a software engineering background, and it was quite difficult to get my head around. I got to the point where I'm like, I didn't feel comfortable teaching it because it was very challenging, and I was asking experts all across Facebook of like, hey, am I doing this right? Because it doesn't feel right. And I'm like, I'm trying to do it like this, like with, and long story short, I changed that out. It is definitely something to consider, but I like to teach and start simple, and then build better as you need better. So we're going to actually be looking at threading and multiprocessing, modules that have been around in Python for ages, 2.7, potentially 2.6. But if you do want to experiment, your VM has Python 3.5.1 installed, which has all the brand new hotness, such as async IO. So you can experiment there. But looking at threading, so this is a module that in Python lets you interact with and use native threads from the underlying OS to help you think of it as multitasking a bit. So some of its pros in Python are a very simple API. I gotta say, I like the fact that you can start a thread with as simple as 2 or 3 lines of code and suddenly now do more than one thing at a time, with quotes around it. Threads are pretty much one of the more lightweight options in Python when you compare them to something like multiprocessing that we'll go into. And one of the nice advantages when you start talking about simple scripts is that they actually can share memory with the parent. And we'll go into that in just a minute, but it means that you don't have to do anything complicated to keep track of or exchange information between the two. One of the cons that you might hear come up in arguments is that threading does not offer true parallelism in Python in specific, because all threads are actually tied to or restricted to a single CPU. So if you have 48 processors in your high-end server and you're running this code with Python and you're using threading, you will use at most 1 CPU if it's all based on threading. That's not a deal breaker in every case, but it is something to know about. Now, granted, it hasn't been that much of a problem. Like, there are cases where it is a deal breaker, but for our FBAR, we actually do use threading, and there's other ways around it. So I'm bringing this up, though, because it's often a point of contention between people that hate Python, which you may run into. And just be aware that there are different use cases for different ones. For example, threading works pretty well when you have IO-bound tasks, meaning that you're waiting on network devices to do things. You're running SSH commands, you're waiting on output, or you're waiting on disk IO for a database. Even though you're sharing a CPU, you're not running one function at a time or one thread at a time. You're running one piece of underlying Python bytecode at a time, so there's a bunch of switching back and forth. So it makes basically a way to appear as things are running in parallel, which is what we showed in the initial demo. Now, comparing to something a little heavier, multiprocessing. In Python, it has a simple API as well, and this is just the multiprocessing module. It actually is modeled just after the threading module. It does let you use true parallelism by splitting across all the available CPUs, but it comes with some downsides that I definitely want to point out if you're getting started new here, because I learned this the hard way, in that it's based on this model called forking, which means if you have a long-running piece of Python code and you use multiprocessing to go do things in the background, at the point that you create that new process, where you say process.start, and we'll see some code similar to that, all of the current code and all of the current memory is copied to the new one. So if you've consumed 5 gigs of memory in the current process doing something, that is now copied to the new one, which on top of that bloat leads to really dangerous situations such as stale state, bad database connections, and so on. So be aware of that, in that even though threading is not truly parallel, there is a very huge hit to moving to multiprocessing that, depending on the workload, is something to know about. So, and finally, not sharing the memory with the parent is something to know about. So for example, with dictionaries in Python, there is a way. I actually thought this was all dictionaries, but I was corrected the other day by a teammate. But in one system I work with at Facebook, we use threads, for example, to split across parallel work across devices. And so we have this idea of a job has sub-jobs for devices. And so it basically keeps track of what's going on in the threads by having a dictionary where the key is of the first level is the job number. And then that value is actually another dictionary that represents each device or each thread. And so then we have a sub-dictionary that is the device name. And so when it finishes running, each individual thread just updates its respective position in a dictionary that's shared globally. That might sound complicated, but it's actually really clean from a code perspective because it means that you're not exchanging data back and forth, and you're natively accessing just data at the top. The alternative to that is you can use a database to talk through things, which is another way we use at Facebook as well. So we're going to walk through this demo now with showing you how to use threads and getting started with there, because it's definitely a very useful thing. Think of like code upgrade tools. Think of like running commands against your devices. It will make things definitely a lot faster than one by one. So to do this live, we're actually going to switch back to IPython. So to get started with threading, we'll import this module called threading. Import threading. And in terms of slides, if you are following along on that one, I am roughly on slide 108 right now. And so to create a thread, when I mentioned it as a simple API, this is actually one of the really cool things because you can do it in literally like 3 lines. And so if we're looking at our one event, we have one event right now. If we want to run that in a thread, we could say thread equals threading.thread, and we just simply pass it in 2 things at minimum. Something called a target. And so what target mentions here is what method or function to go run once this thread starts. We're going to tell it to go run that process event function. And the second thing that is also required is this keyword of args, where we say args equal. And in this case, this is how we're going to pass in the event or the input to that function of process event. And so something interesting here is I'm using target equals to say what to run, but this is not directly running it yet. Because for a function, I would add an open close parentheses to actually run or call the function. But right now, I'm just saying what name that function has, which is basically a variable pointing to it, which then the thread will go look at it and try to run. This is actually all you need to do to create a thread without starting it. And then to start it, we just say thread.start. Now, since there was nothing being printed here, it doesn't look like I'm doing anything right now. So let's show you a slightly different way. Let's say for event in events. Let's build that again. Thread equals threading.thread. And I want to show you there's a way to see what threads are running, which is what we're going to look at. But I want to get a few more threads running so that you have some actual data to look at. So we're going to say for event in events, thread equals threading.thread. And again, point it to the target of process event. And then give it the args of a list that contains that event. And one thing to note, this does expect a list of some sort. So even though it's only one event, we do need to put that in that bracket notation. And then we'll just say thread.start. Cool. So we have no real debugging other than a few. Well, oh, that's cool, actually. So since we have some printing output in our remediations from yesterday, we do see randomly we are getting output from some of the light level remediations that are getting picked up. So that's kind of cool. The other remediations did not print anything, so they're just randomly sleeping. But how do we check now to see what threads we just ran, for example? Well, the threading module gives you 2 ways to look at that, which is kind of cool. For example, we have threading.activeCount, which is a function that we can run to see how many threads are still running right now. Now, it shows me 2 because we walked through that for loop. We ran all those remediations, and then we finished. And since there was no more work in that function that we were running, with the function of process event, the threads terminated. So they're actually no longer running. So we see 2 threads right now, though. So to see what those threads are, we could say threading.enumerate. And that gives me back a list of the current running threads. We actually see 2 because IPython is running one in the background to save our history that we see right here. So that's kind of cool. But let's start making this faster. Let's start actually putting this to use. Because right now we still haven't done that much. So let's change, before we make this faster, let's actually change process events so we can get a little bit more debug output from it. So we're going to just rewrite it real quick. Def process event. It's going to, again, take in that event. And we're going to just fetch back that class, mapping.getRemediation, event.errorCode. And then we'll get back an instance of that class for this remediation, using remediation equals class event. And then now, since we're going to be running this under a thread, it would be nice to add into our debug output what thread is running that. Because you can actually name threads. Or by default, they have at least a number that represents them that we can use to keep track of things. For example, if our system crashes, it would be nice to know maybe how many were running when it crashed, to give you an idea of finding your upper bound, for example. So we could say and get that by saying tname equals threading dot current name, or sorry, current thread dot name. And so now we can, to add our debug output, we could say result equals remediation.run. And then we can print some data that might be a little bit more useful. For example, the thread name, followed by the remediation name. And we might want to know, for example, the device name and the result. Cool. And then we'll just test that real quick for 1. And we see 1 remediation is running in the background, and it gave us some data. So cool. So now we can start building this a little bigger. So if we walk through and look at our event list again for event in events, we can then bring back our friend of creating threads using thread equals threading.thread. We'll give it the target to run, again, of process event. And then tell it, again, what the arguments are, which is event. And then start that using thread.start. OK, cool. So if you got to that point, and that was from slide 114, if you got to that point, you should see a bunch of output on your screen. We're starting to get there, because now we at least kicked off a whole bunch of threads that are doing some work in the background for us. For anybody following along, did you get to that point? Cool. I'll take just a moment to let people catch up. So looking at this, we have on the left side the thread name. So for example, thread 1996. 1996 represents the current number. So if you're in a program and you spawn off threads and then they die and then you add new ones, that number just keeps incrementing over time. So even though we have 1,000, we actually kicked off that round twice in the background. So what we see here, though, is we have the thread number, the remediation name, followed by the device name and the true or false. OK, so I just showed you a really bad example, actually, of something you should not do in production. But I wanted to show you first what you might run into. So what I just did is I fetched the first 1,000 events from my database. And then I just randomly, in a for loop, spawned a thread per event. Thankfully, my database query limited me to 1,000, but it could have been set to 20,000. There is an arbitrary limit where this actually starts hurting you. Not an arbitrary, there's a limit where this will start hurting you. And it's going to depend on what your workload is, again, because you have the one CPU running these. But I would caution you against writing code that arbitrarily runs an unknown number of threads, because you want your system to be predictable. You want it to be stable even when your network is unstable. So we can do a little bit better by using the idea of a thread pool here, where we set up a predefined number of background workers or background threads that are just fetching work periodically and then running them. Granted, it won't be as fast as running 1,000 every time we get 1,000, but it will be a little bit more consistent, and we can then build a system that at least we can start relying on. At this point, are there any questions, though, before we go into the next part? Cool. Everybody's still awake. There's plenty of coffee around. Cool. OK, sweet. So let's take a look at that. So in terms of slides, we're basically on 116 right now of creating a thread pool. And so what we're going to walk through is doing that again with IPython. We're going to separate this idea. So what we built just now was a function to run the event, def process event. And we fetched the list of events from the database using that lookup. So we're going to change it a little bit. And now we're going to describe, instead of running the process event directly in that thread, we're going to build a different method that's handling fetching events and then sending them to that. For sanity's sake, we're just going to call that something different, because process event should represent one event. So I'm calling this event handler. And so on the slides, this is 117, the code that we're about to write. So to do this, we're going to create a new function called def event handler. And so this event handler is representing one of those background threads, and we'll have multiple copies of this running to represent how many we work on at a time. So here we'll say def event handler. And so we're going to change this up slightly, though. Instead of passing an event to this, we're going to give it a reference to a queue to go get events. So let's give it a different input of event queue. And I'll describe that in just a minute. But it's basically going to be a central place that will handle sending and receiving data back and forth to these. And so one trick, so what we're building, though, now is a background thread that's going to continuously get events. So one simple way to continuously get events is to just use a while statement here. We could say while, for example, true, which in Python would be an infinite loop until this program is basically turned off or terminated. We could say while true, event equals event queue.get. And I'll show you in a minute where event queue comes from, but it is actually out of the queuing module, which happens to have a put and get method for adding data to it and retrieving data from it. And think of this as just as a first in, first out queue. And so we grab back an event as they become available. And now we go try to run our process event method that we previously wrote. Result equals process event. And then we just pass in that event to that. And so that's going to run the event. But since we've already got a database here that has the events, it would be nice to go tell the database, hey, I finished working on this one. So that way, you don't, if this script starts again, you don't just rerun everything and spam yourself. So there is a module in there. So what we're going to do now is just open a database connection using that with statement again, with DB, big D, lowercase b, and then we'll just give it a name of dbcon to represent this connection to the database. And then there's a method there that says update result. So dbcon.update result, and it takes in two inputs, the event number and then the result code. So to pass it in that result code, or I'm sorry, the event ID is the first thing. We would pass an event.event ID. And then the number 2 here represents finished. But based on what you build, it could be any number of your choice. So I'll pass in the number 2 to say I'm done with this. Because our initial lookup that grabbed the first 1,000 of events was based on the query of status code of 1, which meant new events. And we're using numbers here instead of text. You might ask why. It's just simply, when you're starting to talk about databases, it's a little faster to use a number for something that is not going to have many options like that. And that is actually the extent of just this function. Once this function starts running, it'll have an infinite loop where it'll fetch an event using event q.get. It'll run process event, trying to figure out a remediation and run the remediation, and then it's going to save the result. For everybody following along, did you get to that point so far? Cool. So now let's actually start up our background pool of threads that's going to be working on these events. So we're going to do that with, well, actually, I skipped a step. So we're using this event queue. We need to first define that. So it's not actually defined, but we'll need to use it. So we're going to import this module called the queue module. And from that, we're going to grab back an instance of queue.queue. So event queue equals queue dot, and then this second one is an uppercase Q, queue. And that gives us, by default, a first in, first out queue that module is going to manage. And it's actually playing some tricks on us, which go back to some of the topics I mentioned earlier, in that it's going to manage one queue that all of the threads are going to be interfacing with. But don't worry about that. Just trust that the module will do the right thing there. So we have one variable called event queue. We're going to now spin up a number of threads in the background to work on these remediations. Let's start a little bit small. Let's say we want to start 10 at a time just to help make the output manageable. So let's say num threads equals 10. And so to start these, we could say for num in range, which is just a handy a Python method that gives us back a list of whatever number we pass it, range of num threads. We're going to now create a thread that represents one of these for the event handler. So we're going to say thread equals threading.thread and pass it again the target, but this time the target's different. This time it's what we created just above the event handler method. Target equals event handler, args equals, and then in this case the argument is no longer the event because we're actually passing it now the reference to the queue, and then the individual background thread is going to go grab events from the queue as they become available. So we'll say args equals event queue. And then we'll just say thread.start. OK, so at this point, we should have those 10 threads running. We can then, again, use our handy lookup methods from the threading module, for example, threading.enumerate. And now we do see back a list of these threads that are running. We did not name them, so they're just going to have, again, numbers on them. But you can see that they are running and they're waiting for work. So let's start sending them some work. So we have that list of events. So for example, let's now change the way we go get those events so that we can make this all run in real time instead of running one by one as I hit enter. So first, let's turn that database lookup into a quick function. So let's create a function for def get events, which will not take any inputs right now. And so what we're going to do now here is open the database connection with db.db as dbcon events equals db_con.get events by status. And again, the number of 1 as the input there represents new events. So since we're updating events as we finish them with 2, that means that when we run this again, we're not going to get those back. We'll just get back what is left. Which is good to know, because that means as you play with this, you have 3,000 or so pre-staged. So at some point, you will stop fetching new events and need to actually start up one of the scripts. And I can show you that in a minute. There is a script to start all the things I just opened earlier in a tab to make that easier. So what we get back, though, is with db.dbcon as events, we get back the list of events, and we just simply return events. OK, so now we have a function to go get events. I bring back now my handy while loop. And I just say while true, which there's ways to make this better, because at some point you may want to catch when you're actually shutting down, for example, which I'll go to in a minute, though. But let's say, just for simplicity, say while true until it stops. While true, events equals get events. And then for each event in that list of events, we're going to now populate that event queue using event queue.put. And then we'll basically put the event into it. If you're following along, have you gotten to this point? Because once I hit enter, we're actually going to get a bunch of stuff go on screen. OK, cool. So if I hit enter, actually, if I hit enter twice because of IPython, what I'm going to walk through is I'm going to get 1,000 events. And for each of those 1,000 events, I'm going to add them to the queue. I have 10 threads running in the background, so I'm going to process 10 at a time. But that last while loop I mentioned is going to grab 1,000 at a time. So I'm actually going to flood that queue really fast, much faster than I'm going to work on. But that's OK, because if I can build this reliably to run at least 10 at a time, and honestly, I would say start out with 100 once you are comfortable with how to debug this. 100 is definitely a reasonable number of threads to run, and it's a common thing we start with on our own systems. But I would caution you about running 1,000, because as you start to run 1,000, you're going to run into some other issues based on what you're doing. Which, yeah. For example, so what we see, though, running right now, we have our 10 remediations at a time running. What's interesting to note here, if you actually look in the code for the default remediation, which I want to show you, so if you look in the default remediation, it is actually like using the time module randomly up to 15 seconds. But I'm not waiting 15 seconds between each of these. So what I wanted to show you here is the fact that even though you're in Python with threading, there's this misconception of that it's only one thing at a time. It's not really one thing at a time from what you're typing. It's one thing in the machine level. So I'm actually running and managing and context switching back and forth 10 different things here. And as they're sleeping, I'm waiting and going and sleeping in the other one, and I'm going back and forth. So as I run a command against a device with SSH, Python and the interpreter underneath are going and running another command and waiting for that output. So it still gives you a way to run all of these in parallel. And in that original demo, I was running 100. So what I wanted to give here, though, is more food for thought of how to start building this. So granted, what we just built in IPython still is not a lot of code. But at this point, we are fetching remediations from an actual MySQL server on this VM. We are actually trying to run some sort of remediations against them and potentially log in a result. Now, as you start to think about building this bigger, there's a few things that we definitely could think about. For example, right now, I'm looking at this on my terminal, which is cool because if I print error messages, I can see that. If I'm running this on a remote server, I have no real visibility to what's going on. So that's where making it a little bit more user-friendly helps. For example, building CLI tools separate that let you interface with the database to say, what remediations have I run today? For example, reporting tools that are kind of extras, they come in handy here. And this is where also keeping track of your log messages makes sense, because right now I'm printing on screen. But it might become useful to log those either to a file, or depending on the verbosity, I would actually definitely consider logging to your database if you have a reasonable install of MySQL. Because searching against a database for log files is surprisingly fast. And it's actually something that we use at Facebook that in this kind of system makes or breaks how much time you have to spend debugging when it breaks. Because if you have these logs, for example, in a database, you could run a quick CLI tool that says, show me all the logs for this device, or for this device at this specific remediation number, and so on. And you can start quickly filtering through what it evaluated, what it compared about, and so on. So I only showed you bits and pieces of this. But there is actually a lot of example code that is on the USB key that I want you to be able to look at and digest. So if you look through that, it's a little bit bigger of a piece than what we just showed. So for example, I think I might have just frozen it. Anyways, So sometimes your while loops are a little too aggressive, and I think I just froze my VM. But what I wanted to show you, though, is if you browse through the code, take a look at, under the 201 code, netfbar/lib, or not lib. Actually, lib is where the remediations are, but the other directory is the event processor. That gives you some other examples to build on. For example, I'm using while loops right now, but in the real example, I actually catch when you press Control-C, and I properly terminate the threads, which is something to think about. And there's just some other examples in there to run with. That kind of leads to my, where'd you go? Oh, cool. Only the VM's frozen. Sweet. So that actually kind of wraps through what I wanted to walk you through and show you. And then there's a few final steps here. So looking again back at what we were building, we're trying to build a system here that is not Facebook proprietary. We have some of our new devices that we're building on the FBAR side, but we still have plenty of vendor devices, and they're not going away. Because honestly, it's a lot to build. So we want a system that works for everything. So for example, all of our normal devices send syslog messages. We still aggregate all of those syslog messages centrally. In the case of what we built today, we built the second piece of this, the event processor. We also have this parsing engine that we looked at yesterday. So as you start to think about how to build this bigger, though, it can become more distributed. So one thing that's kind of nice when you start looking at using MySQL or just database servers separately is that it gives you a nice clean line to separate things. For example, I can apply changes to the parsing engine without affecting the remediations. I can add a remediation and restart that piece without affecting the parsing engine. But as you start to think about a bigger network, one syslog server may not be enough. Probably isn't enough. And in the case of what we use, we distribute syslog servers across different data centers, different regions, but we distribute it in a point where we don't care that they're separate. Devices locally send to the local syslog server, and then agents scrape the local syslog server and populate the database directly. And then other instances or other pieces of code just go talk to the database. They don't need to know about the other pieces. And depending on how you break this up, as you want more volume, this is where threads are not evil, because if you get to the point where it is a problem, it probably makes more sense to run more than one instance. So in our case, we basically have maybe tens or hundreds of instances of that event processor. And maybe they're only fetching their local data center or specific types of devices to act on. And they're kind of breaking up the load that way. But we use a database in the middle to kind of communicate between the two. And it gives us a nice line here. So again, our goals today were to build something organized and show you a way to get started to support hundreds of remediations. Fast enough to react to hundreds, using just some simple concepts of threading, and give you some ideas of what other things you could look at. And finally, hopefully this was simple enough to follow without any software engineering background. If I lost you, grab me, because that is definitely the goal of this is to manage it by your network team and your NOC and everyone. Because you want everyone to build and support this together, not just a software engineer. So before I leave you with the final takeaway, on the USB keys, we have randomly marked a bunch of them with silver dots. If you have one that has a silver dot, you've won a prize. We actually have one of my favorite books up here, Python 3 Object-Oriented Programming, that we're going to give away. So definitely stop up here up front to get that. One other thing to point out, for next NANOG, we're trying to organize potentially a hackathon where we take this idea of building things together. Either it would probably be something totally different at that point, but build some tool together through more of like a half-day or full-day event. So if you're interested in that, we have a group called NetEdge Code on Facebook, group/NetEdge Code. There's a poll there. We're looking for ideas on both what kind of content you want and also what days might work best. And finally, thank you for coming. And just think about what would you do if you're not afraid. Thank you. Oh, and questions, but yes.
Cody from Yelp.
Yeah.
Is there a reason to use MySQL as kind of a queue versus something like RabbitMQ or ZeroMQ or some other thing that traditionally does that? Do you keep events long term, or do you like pull them out of the database once you process them?
So we typically use MySQL as the queuing. All the systems that actually are using MySQL, it's permanent history. it's persistent. I'm screwing this up. So we keep them forever, basically, which actually helps in terms of analytics, in terms of debugging things, because we have like CLI tools that can let us go say what is the history on this device, and being able to go back a year or 2 years comes in handy when you start thinking about repeat failures, because we don't consider repeat failures right now in this system or in our real FBAR. It's actually one of our current flaws that we're trying to figure out how to build. But having that history is kind of nice because when you see one event, like it might be a module going down, but if you have the same module failing every month, you might have a backplane or something else that's actually causing that failure. And it's nice to do that. But in terms of your actual question, we do just use MySQL as the queue there.
What do you do for marking an event so it's not processed again?
Oh, so right now this demo just used a code of new and a code of finished. Okay. In the example code, I actually put together another one that's like active. I think we end up actually using something like 3 to 4 codes based on where it is in the pipeline, for example, as it goes through different components.
Okay.
Yeah.
Thanks.
Well, cool. Well, thank you again for attending. I know this is the last session, so it's obviously a little harder to stay around. But thank you, and feel free to grab any of us if you have any questions or any follow-ups in that group. And again, if you won one of the books, definitely grab us at the front too. Thank you.